Okay, let's get started. The first exercise for this lecture is exercise 16.1, which is the one sector model of growth, the basic neoclassical growth model, which now we are trying to interpret as a competitive equilibrium. We know from exercise 5.1 that there is one optimal capital and consumption and the related consumption path. So all we need to do now is to check if assumptions 15.1 up to 15.5 hold, because if they do, then this Pareto efficient allocation can be interpreted as a competitive equilibrium. Okay, so let's go, let's go one by one. First, assumption 15.1 to any I, the consumption set is convex. Because to any I is the positive orthant of the space L infinity, this assumption trivially holds. So we are good. Assumption 15.2 is the next one. To any I, if x and x prime, if they are in the consumption set, and this relation between their utility holds, and we have an appropriate weight or constant, then the convex combination of these 2 points or series consumption path, their convex combination is also preferred. Here we need to demonstrate that the utility function is concave, and this is a question, this is a problem which we can solve on the basis of the concavity of the one period. So idea, concavity of the one period utility function. Given the fact that to all indices we have the same preferences, we don't need to pay attention to the indices, so we can work by we can work in a slightly simplified framework. So let x and x prime to consumption path in x such that consumption path x is preferred to x prime. And as a next step, let's create their convex combination. What we need to show, what we want to show, is their convex combination is preferred to the less preferred consumption path, which is not too difficult. In an expanded form, This is what we have. This is the one period utility function. Okay. Given that the one period utility function, is strictly concave, to all t, we have that so this is the consumption path in the convex combination. So this is what we have to all t. From this, we have, from the strict concavity, we have this inequality. Okay, which is equal to the convex combination of the utilities of the two different paths, which, to be more specific, you can skip this step. I'm just trying to be as specific as possible. Okay, so this is what we have. And given the fact that by assumption this inequality holds, it is true that finally we have this relation. So in sum, the utility of the convex combination of the consumption path is preferred to the less preferred consumption path. So assumption 15.2 holds. We are good. Okay, assumption, next step. Assumption 15.3. We have this utility function, and it is supposed to be continuous. Just like in the previous step, in which we demonstrated the concavity of the utility function, we are going to demonstrate the continuity of the utility function on the basis of the continuity of the one period utility function. So formally, this is what we are going, so if then, so by reducing the distance between two consumption paths, we can reduce the distance between their utilities. Okay, so what does it mean? It means that this inequality holds to any t because of the subnorm oh geez. So the norm that we use in this space is the subnorm. So it means that to any t, the difference between the two consumption paths in any period is less than delta. Given that u, the one period utility function, is continuous, we can find an epsilon, a positive, a strictly positive epsilon number such that given this distance to OT, then oh geez, I don't have enough space, but it's just a minor setback. Then it may seem odd, but we need this formulation of the distance because of the discounted sum. You will see the point in a split second. And now we can say the following. So if we have this distance between the two consumption paths, we can say that this equality holds. Okay, this is just the expanded version of the difference. Okay, it cannot be higher. Is the usual trick, the usual step in these exercises. It's very common to utilize this inequality. And this is the point where we are going to use this formula. So this sum oh geez, this is an infinite sum which is equal, this is a geometric series, so this is epsilon. So u is continuous, the utility function is continuous in this norm. Okay, so in the norm we use assumption, next one, assumption 15.4. The production set is convex. This is the aggregate production set. This is supposed to be convex, which we are going to show by playing on the interpretation of this convexity, meaning that if we have 2 points in the production set, then their convex combination is also in the production set. So this is the idea we are going to use. So first, let's start with the definition of the production set. The production set consists of production path in the positive orthant of the space L infinity, such that there exists a capital path in the same space, supposing that we have an initial value and, most critically, this inequality holds all t. So this is the definition of the production set. So there is interpretation. There is a capital path K such that if the initial value is a given, if the initial value is given to all t, the inequality holds. So this is the way we define the production set. So in sum, any path y is in the set if it satisfies the inequality. I mean this inequality. So this is what we need to demonstrate that the production set is convex. Okay, so the idea. Let's pick 2 different capital paths with the same initial value So we have 2 different paths for the capital stock with the same initial value. It means that the 2 paths are different. The related production paths are also different. Okay, because okay. Okay, Alt T. To show this, to realize this, we only need to realize that we need 2 different consumption paths. So we assume 2 different consumption paths. All right. So we have y and y prime, two production paths. They are in the production set because they satisfy the inequality. Let's have the related convex combinations in the following way. We have the convex combinations of the capital path and the and the production path. Okay. We know the following. On this basis, we can say the following. If we add up these two convex combinations, we have which means that here comes the trick. And given that they are in the production set, both paths satisfy the inequality, so this is also true. And because of function f is strictly concave, we have this inequality. So in consequence, we can say that this is true. So given that the convex combinations satisfy the inequality with which we define the production set, the convex combination is in the production set, so assumption 15.4 holds. And last but not least, let's have a look at assumption 15.5. The production set has an interior point. The idea, let's find a path, a point in y, which is in in the production set, so we need a point of which we know that it is in the production set. So let's find a constant, an appropriate constant capital path. It means that it is in the production set if it satisfies this inequality, which means that to all t, this inequality must hold. So we need a sequence that satisfies this inequality. Okay, so specifically, what about this path? This sequence is in the production set because it's lower than the upper bound. So it's in the production set. And it's clear that this inequality also holds. So this is all we need to see that this capital path and production set, this production path is in the production set. This production path is in the production set. Okay, so given that the capital path is constant, this is constant. So this is also constant, unchanging, I mean. So we need to find an appropriate, strictly positive number to which every other production set is in the epsilon ball around y. Okay, so this is the idea. So we have a constant production path, and this is the zero line. So somewhere in between we have this production path. This is also constant. So if we have another constant path given this way and another later, so what if we pick epsilon in a way suggested by this figure. So what we need to demonstrate is even if epsilon goes to the upper bound, then we have production path that satisfy all the resulting production paths satisfy the inequality. So, on the one extreme, on the one end, this is easy. So this is the production path which we receive with this epsilon, which is strictly lower than the upper bound on the production set. So in consequence, we say that any path in this range satisfy okay. So it's in the production set. On the other end, let's find production paths under the constant path within the given range. We play the same game. Which satisfies the inequality what we need. So in consequence any production path in this range satisfies that inequality on the basis of which we define the production set. So to an appropriate positive number, this ball is in the production set. So we can find interior points in the production set. So the production set has interior points. So assumption 15.5 holds. what we can conclude is that all the necessary assumptions underlying theorem 15.4 hold. There is a linear functional phi which we want to interpret as a price system. The existence of this linear functional is ensured by 15.4. So the last thing to check is the remark of the second welfare theorem, which helps us to find a competitive equilibrium. So to check if the remark holds, we need to find a cheaper point. A cheaper point is needed. This is the Pareto efficient allocation, and as compared to this Pareto efficient allocation, we need another allocation which is cheaper, measured in the linear functional. Okay, so we know definitions help. We know that in the sequence, the optimal sequence, because of the definition of the consumption set, we have non-negative elements. So on this basis, we want to consider what we know about given that this is true, we have non-negative elements in the consumption path. What can we know about the linear functional? So what do we know? What can we know about this price system, possible price system? We can rule out the possibility of negative prices to any t. Prices are zero or strictly positive, because if to any t the price were negative, then we would violate the two conditions underlying theorem 15.4. In short, according to theorem 15.4, a consumption path with higher utility would be cheaper if we had a negative price to any p. So this is any pi. So this is the reason why we can say that the price to any period is strictly non-negative. Okay, so we have two possibilities on this basis. The value of the Pareto efficient allocation is strictly positive, or it is zero. So let's check these two cases. In this case, we have two options. The optimum path is the zero path, or the linear functional is identically identically 0. This is not possible because of theorem 15.4, and this is also not possible because it is not optimal, because the utility function is strictly increasing and there are possible consumption paths which are strictly positive. So we can exclude this possibility. So this is the case in which we can think. So to the optimal consumption path, the value is strictly positive, and given that this consumption series, the 0 series, is available, and the price of this consumption path is strictly 0, and given that the optimal path is strictly positive, this is the cheaper. This is the cheaper path that the remark requires. So we satisfy all the assumptions underlying the two welfare theorems and the remark. So we have, in sum, the Pareto efficient allocation is a competitive equilibrium. In the next step, we are going to check two further assumptions, assumption 15.6 and 7, and we will try to find an actual price system to this competitive equilibrium. It's gonna be very instructive. In part C of the exercise, we are supposed to check assumptions 15.6 and 15.7. As far as the former is considered, assumption 15.6 means that a truncated sequence remains in X or Y respectively. This is trivial given the fact that the 0 sequence is in both the consumption set and the production set. So any truncation of any feasible consumption and production set to any capital T remains in X and Y, the consumption set, or in the production set respectively. So let's put it formally. Let a production path is in the production set. It means that this inequality, the defining inequality, holds. However, we want to realize we are supposed to realize that this inequality also holds. So this inequality also applies, because of which consequence the 0 consumption stream or production stream is also in the production set to any capital T, meaning that any truncation of a feasible production path remains in the production set. So assumption 15.6 holds. Assumption 15.7, it regards the preferences. So if we have two consumption paths in the consumption set, and the one is preferred to the other, then to sufficiently large T, capital T, the truncated version form of the preferred path remains preferred. So the truncated sequence remains preferred. How to show it? Let's use the discounting in the preference system. Let's have a strictly positive epsilon. Given that U is bounded, we can find a specific period to which this holds. So by appropriate truncation, we can make this inequality hold to any T above this threshold. It holds to any consumption path in the consumption set. So on this basis, we can say the following. So this is the utility, overall utility of two different consumption paths. Which is the same, which remains the same if we add and subtract the same number. Okay, and please note that this part of the equality can be rewritten. This is a truncated sequence. So we can put this part of the inequality in this way. This is the zero sequence. Which, as always, cannot be higher than this sum. All right. And from this it follows and this is something we can make good use of. Because we can find an appropriate T asterisk to the zero sequence too. So we can find okay. So it holds. Okay. So from this, so we just applied the previous fact, the fact we have just established. So from this inequality comes. And given the fact that epsilon can be reduced to any low level, we have the following fact. And given that this inequality holds by assumption, or in other way, it is true. So this inequality holds to any strictly positive epsilon, but epsilon can be reduced to any level. So in sum, we have that the truncated sequence remains preferred if we can find an appropriate t. Okay, so to know that theorem 15.6 holds, we need to pay some attention to the non-satiation condition, which is satisfied non-satiation requirement in theorem 15.6, which is satisfied by the fact that we have this commodity space, and u, the one period utility function, is strictly increasing. So once again, the non-satiation requirement holds. So we have a linear functional that can be interpreted as a price system, which we will work out in the next step. So we will show that it has an inner product representation. So this is the next step for us. On this basis, we want to learn more about the price system, the existence of which is predicted by the two welfare theorems. There may be problems because the product space is the positive ortant of the space L infinity. So any linear functional that can be interpreted as a price system, so that has an inner product representation, it must be in the dual space of L infinity. So it must be in L 1 in order that we could interpret it as an inner product. So this is what we are going to check. First, we will show a price system, a seemingly appropriate price system that later, as a next step, we will check if it defines a continuous linear functional in L1. So the first step, the budget line of the problem can be described in this way. So this is the budget line, the budget threshold. The right-hand side, this is the income of the household's income from the firm. In equilibrium, an interesting fact, in equilibrium, the consumption paths and the production paths are equal to any t. So given these facts, the household cannot finance any consumption path which is above the budget constraint, the budget line, the budget constraint. So this is not possible. So what is possible is buying a consumption path on or below the budget constraint. It is interesting because this inequality gets us to theorem 15.4, because if we have such a price system, then we have a price system that satisfies theorem 15.4, because the zero sequence is a possible sequence. So if we had an appropriate price system, then the remark would also be satisfied. Okay, the textbook suggests an idea. So let's try to define the price ratio between two consecutive periods as the reciprocal of the of 1 plus the interest rate. So in this reformulation of the problem, this is the path of the interest rate. This is not a new variable. This is just a variable on the basis of which we can describe the price ratio between any two consecutive periods. In other words, the change in the price level. Okay, so this is the idea suggested by the book. What we want to expand is the budget constraint of the household, which can be rewritten in this way. Hopefully it's gonna be correct. by simplification dividing the two sides of the inequality, we get the following structure. Okay, and we also know that in general which leads to the specific equality. So on this ground we have a very nice recursive formula. For instance, this price ratio can be rewritten in this way, or we have longer chains. So any price ratio can be reduced to the products. So we can rewrite the budget constraint it's gonna be long, but it pays. So you can realize that these are the price ratios of the consecutive periods. So this is the reason why we can apply this beautiful recursive formula. I believe this is the most beautiful part of this theory, when you are supposed to find recursivity in the sequences. Sometimes it's complicated. Sometimes you need my experience. Sometimes we need MATLAB. We need to work in the symbolic math toolbox of MATLAB, because sometimes when the recursive formula is too complicated, we can make errors, and rewriting the expression in MATLAB in symbolic math, it can help. So in sum, we have the following formula for the budget constraint. the same on the other side of the inequality. Okay, so on this basis, we can turn to part D of the problem, in which we should express formally the price system. So we have the sequence of the interest rate to describe price dynamics, and on this basis, on this ground, we want to describe the path of the interest rate, because this path will define the path of the price dynamics. If you check the solution manual of the exercises, then you can see that we should work in the Lagrangian framework. This method is not frequently used in the textbook and in the exercises, so I urge you to check Tom Sargent's 1987 textbook entitled Dynamic Macroeconomic Theory, especially around page 14. Okay, so I am going to use Tom Sargent's framework to work out this problem. So to write the Lagrangian formulation of the problem, we need to realize that we have three variables in the problem. Okay, so the capital path is determined by the production, output, and consumption. Okay, and in the general framework, this is this functional relationship holds. So ut is the control variable or decision variable, which is supposed to be sales in period t. And on this basis, there might be other possibilities, but I used this formulation. So let's try to expand the Lagrangian function on this basis. So this is xt plus 1. So we are identifying the variables. So, okay. So let's try to expand the Lagrangian formulation of the problem. On the basis of Tom Sargent's formulation. And here we have a multiplier to each period, just like normally. and so on. So we need the conditions. So we are going to derivate the Lagrangian function with respect to the control variable to all the periods in the next period. This is, and so on. So in general, we have this first order condition. Okay. This is okay. And we also, following Tom Sargent's treatment and formulation, we also need to derivate the Lagrangian function with respect to the state. In general, this is what we have. Oh geez. Okay. The marginal product of capital is the ratio is equal to the ratio of the multiplier, which can be put in another way. So this is what we have. So the interest rate is related to the marginal product of capital. And given the fact that we have only one Pareto-optimal capital path, the path of the interest rate is given by this unique path, and on this basis the price dynamics is also unique. Okay, so there is a unique price system. The household, we will use this part of the formulation later, so it's gonna be useful. So this is what the household wants to maximize, the discounted sum of the one period utilities This is a dynamic problem as compared to the firm's problem, which is a series of static problems. So this is the reason why we had distinct multipliers to any periods, to the periods, because the firm's problem is a series of static problems, but the household's problem is a dynamic problem. So the household has a dynamic budget constraint. Okay, with a single multiplier. All right, I think it's correct. So the first order condition is this equation. In general, and we also know that to the unique capital path, a unique consumption path belongs. So a unique optimal Pareto efficient consumption path is a part of the problem and its solution. So we can have the unique path for the interest rate on the basis of the problem of the household too. So in sum, given that the solution to the problem is unique, the price system must also be unique. And there is one final step I want to take, because in a minute it's gonna be very useful. Please don't forget that we are supposed to show that this price system is consistent with the linear functional predicted by the second welfare theorem and the remark. So in other words, we are supposed to demonstrate that this price system defines a continuous linear functional in L1. So this is what we are going to do in turn, and in this regard, this formulation I am finishing off is gonna be very useful. So we have a candidate price system, but we have one thing to do. We should demonstrate that the linear functional defined by this price system is linear, belonging to the space L1. This is what we are going to do in turn. So in the following and final step, let's try to check if the price system we have just defined defines a linear functional that is in L1. So this is what we are going to check, because if so, the linear functional has an inner product representation. So this is what we need to show. How to set out? Let's use the definition of continuous linear functionals found on 444 of the textbook. So a linear functional is continuous if it is bounded in this way. In general, given that the space we use is L infinity, this is the definition of a continuous and bounded linear functional. So this must be finite. So what we need to show on this basis is very simple. This sum is supposed to be finite. Okay, so given the fact that any point in this space, in the space we use, is bounded, we can say that to any point in this space we can find an upper bound. And in this case, this sum to any point in infinity cannot be higher than this expression. Okay, so this is the critical part of the sum, because given that this is finite, to be finite, this sum must also be finite, and this is what we need to check. To this end, we need to use what we know about the prices. So in the latest section of the problem, we used this formulation to describe price dynamics. So there is a strict relationship between the price level of the consecutive periods. So we want to know more about this ratio. From the households problem, we know that this equality holds. To simplicity, let's assume that we are on the steady state path. So, you know, this is just a reminder. In this, this is lame. This is the upper bound of the capital stock. So there is a capital stock in the steady state. So if we are in the steady state, we remain in the steady state, and we want to we want to know more about the consumption path. If we are in the steady state, then the capital stock doesn't change. Oh, geez. So the consumption path is also constant. So we have a steady state consumption path. From this, it follows that this ratio is 1. So if we are in the steady state, this ratio is beta to all t. So in sum, in the steady state, price dynamics is described by this difference equation. So specifically, which is great. So the linear functional defined by our price system is finite. Okay. Here we assumed that we are on the steady state, in the steady state. Given the fact that the system converges towards the steady state, only in a finite number of periods, it is only a finite number of periods that we are not in the steady state, but here, not in the steady state. So there is only a finite number of periods when we are outside the steady state, but here it is also true that the marginal product of capital describes the interest rate, but this must be finite because given the conditions, the capital stock must be strictly positive and finite, because of which this is RT. This is also finite. And it is also true which is also finite. So in a finite number of periods, the sum of the prices in a finite number of periods doesn't endanger the continuity of the linear functional. So in sum, our price system defines a linear functional which is continuous, so it is in L1. So the price system we have found is an appropriate price system. Now, let's have a very short comparison to exercise 16.6, which is very instructive. It's a bit technical, but very instructive, especially if we compare the results to our results of exercise 16.1. Please remember that we find a price system which is any positive constant number all t, so this is a constant path. And in this case, if we calculate if we check if the linear functional that this price system defines, we realize that this is not bounded. This is an infinite sum. And an infinite sum of strictly positive numbers must be infinite. So it doesn't define a continuous linear functional. So this price system is not appropriate. A way out truncation. So we need truncated sequence, a truncated linear functional called psi. We point out that to any consumption path, it is 0. And on this basis, it cannot be the ground for a competitive equilibrium, because even if all the assumptions underlying the two welfare theorems hold, the price system must also satisfy the remark of the second welfare theorem. And the remark requires the existence of a cheaper point. But if the linear functional which we want to interpret as the price system is 0 to any x, then there is no cheaper point, because to any point we have 0 as the value. So it cannot be an appropriate price system. This is very instructive. So what we need to learn on the basis of exercise 16.1 and 16.6 is that even if the assumptions underlying the two welfare theorem hold, they cannot guarantee the existence of a price system that defines a linear functional. So they don't guarantee that that the linear functional is in L1. Okay, this is a very important lesson. So even if, once again, even if all the underlying assumptions hold, then we still need to check if the linear functional is in L1, because it is only in this case that we can interpret the linear functional as a price system underlying a competitive equilibrium. So these were the implications of the two welfare theorems I wanted to show you, I wanted to highlight. Thanks. Goodbye.